So if you try this, I'ma leave the door open. I'ma leave the door open. I'ma leave the door open, girl. I'ma leave the door open. Okay, howdy, Ags. Doors open on one last lecture to complete the circuit. We have a little bit of gap here, right at the beginning of our material about pressure. So we'll get started. This one shouldn't take too long, and then we'll get back into the realm of lectures that were recorded earlier over the past year. The funny thing is, in terms of context, that all of these videos have been recorded under the, I guess, cloud or the challenges of COVID. We're getting closer. So many of us have gotten some vaccines, shots. Hopefully the same is happening for you, and soon we will all be able to, well, either wear masks together roughly in the same place, or eventually get rid of them safely, because right now it's not actually safely. The reason is because the virus is mutated, has a number of different strains, and these are going to be flipping, or in a sense taking over, right around April Fool's Day. And so they're actually a lot more contagious. They are also more virulent, and there's a greater chance of getting sick, etc. So we still want to be careful. Once you've gotten the shots, then we should still wear our mask for a while, maybe quite a while, until we all reach the dreaded herd immunity. But it takes 70% of the population with vaccines or confirmed cases to be able to get there. We'll get there, but it's going to be sometime, well, I'd say this summer, but it doesn't take long around here before it will be summer. So right now it's late March, and it'll feel like summer, well, in a week or two or three. So sometime over the next few months, we will get there. Okay, so they will start with a simple comparison. Which object's bigger, right? So even COVID, even the scary COVID can't change this. Volume is the 3D space occupied by an object, whether it's a softball, baseball, golf ball. A softball, by the way, and a shot put have roughly about the same volume. So 3D space, and not surprisingly, we're looking at meters and feet to the third power. So meters cubed, feet cubed, those are the standard units for volume. So part of the reason we're thinking about volume is that we're going to be starting to look at material properties in the near future, and things like density. So we're going to need volume. We're going to need things like contact area, cross-sectional area, deformation, strain, to be able to quantify and to be able to analyze material properties. And especially important to make a comparison, healthy versus non-healthy, exercise versus sedentary, what happens with rehabilitation, what happens with injury, what happens with aging, etc. Okay, so it's just some very basic terms to start off today. Make it slow, make it easy. Density is the next one. So as I was mentioning, a shot put and a softball are roughly the same volume, but obviously a softball is a lot lighter, easy to toss up and down. Couldn't do this with a shot put because that weighs 16 pounds. So it's a dense material. It has a lot of mass for the same volume. So for example, let's compare planets, the Earth versus Jupiter. Jupiter's a gas giant. It's huge, but it's actually not very dense. So you could probably, but it has a lot of, because it's large, it has a lot of gravity. So near the center, that gas gets compressed. and it does actually become dense. But near the surface of Jupiter, it's pretty light stuff. Okay, so again, a density is basically the amount of mass we have per unit volume. So not surprisingly, the units, well, we'll start with the metric system because these units make sense. They're units of mass divided by units of volume. Okay, so that's why we went over volume just a minute ago. Okay, so in the English system, well, everything's kind of messed up. We're going to use specific weight. So that is the weight, which is a force, divided by cubic feet. Technically, it's not really a density, but close enough. Okay, so again, shot put, softball, roughly the same density. We're interested in density because it can make a difference in terms of how something curves. So a softball is easier to make curve than a baseball because it's a less dense material with less mass. So if you generate through Bernoulli's principle and the Magnus effect, which is basically throwing air molecules behind and to the side, you can make this thing curve a lot easier than a baseball. And if we want to expand that literally, if we look at a soccer ball or a beach ball, because they're not very dense and they're fairly large, they have a large radius, it makes those objects a lot easier to curve as well. In the human body, density becomes important with bones. Muscles technically can have different densities based on the amount of fat in them, but there's no difference in the density of the muscle fibers themselves. You can remember when I was a kid, there was some myth about that, but that turns out to be completely false. The only thing I can really think of in terms of density for muscles would be the amount of fat and connective tissue in that. And that you get more of that when you get older, or if you get heavier, or you have metabolic disease, etc. Now, bones, if the density increases in bones, that's a really good thing because that means that we've been able to deposit more calcium salts into the bone and make it denser and stronger and stiffer and tougher. And that means that that bone is less likely to break or fracture. Exercise training increases the density of bones. There's a marker called bone mineral density. So we use either photon absorptiometry or X-rays or another special type of basically bone analysis type machine, a bone scan, if you will. There's one that works on induction. There's a few of them, but the most common are really dual X-ray absorptiometry, special kind of X-ray, and dual photon absorptiometry. So that basically uses light beams. But either way, whether it's light beams or X-rays, the thicker and especially the denser the bone is, the more it's going to block those X-rays from moving through the bone. And when you look at basically film of a bone, an X-ray, you're getting actually the negative, because in reality, the X-rays or the energy has basically gone on the film, where the bone, especially dense bone, has been able to block that energy. Okay, so the more dense an object is, the greater mass it has per unit volume. Pressure, and we're going to do quite a few applications related to pressure. Pressure is basically a force being applied over a contact or a surface area. So the greater the contact area, the less pressure there is. So if you land with, let's say, your feet, especially as you're running, maybe as a midfoot striker, you're going to spread out that force over a larger contact area. If you land on your heel, you're probably going to have a higher force, but you're also going to have a smaller area. So the formulas for pressure here, and this is not the same as power. The P here is pressure, force divided by, here it's contact area. I might as well write that down. It's the contact or surface area. So in the English system, the units are pounds of force per square inch. It's not standard, whatever. But those technically the units that we use in the English system can drive you nuts. In the metric system, it's newtons per meter squared, and that's the same thing as a Pascal. So pascals are the standard units for pressure in the metric system. Okay, we were just actually talking about rear foot and midfoot strikers. So when you land on the heel, because delta T of that collision will be small, you're going to have a large force. And that large force is exerted over a small area. That means lots of pressure. How can that actually cause issues? Well, quite a few things are going to go on. First of all, there's going to be a higher force acting on the ankle and the foot and even up to the knee. And that force is being exerted over a small area. So that's going to concentrate that force literally and increase the amount of stress. And we're going to talk about mechanical stressing, stress on those tissues. Also, when you land on your heel, especially when you're running, what's going to happen is that that foot is going to plantar flex. When a plantar flexes, that actually shortens the Achilles tendon, the gastrocnemius and soleus and plantaris muscles. So it means that these muscles can't stretch immediately. So they can't, A, protect you from the load, B, they're not able to store that spring force and spring energy that can be used during the push-off. Also, the arch of the foot doesn't provide support. So that increases the risk of an injury. The plantar fascia and the calcaneonavicular ligaments, they don't get stretched either, so they can't store force and energy. So we've got a lot of things working against us. And in addition, let's see if I can do this. We've got this force that's acting downward. Oh, that looks like a boring color. Let's make it a good color. All right, I can hardly see the arrow. Just make it huge. There we go. Okay, so this is the action force, which is going to be down and forward. So with Newton's third law, I'm going to paste it, flip it, because we've got equal and opposite forces. I want to give it a different color. Red's good. Okay. So now we've got a reaction force that's up and guess what? Backwards. So if we resolve that vector, let's see if we can do that. Copy and paste. We'll slow at this, but we'll get it. There's the X component. Notice it's backwards. That's good. And I'll paste again. And we're going to have a Y component. I might as well fix that first. Come on. Yeah, there we go. Okay, perfect. So when we resolve this vector into X and Y components, we can see where the X component is pointing. That's backwards. That's going to slow you down big time. So we've got a large force, especially this Y component is going to be large. You have a reaction force that's pointing up and backwards. That's going to slow you down. You have a large force because if we write in here, little formula, let me move that up. Okay, that's fine. As I look, okay, that's close enough. So this is our impulse equation. The left side of the equation, we have force times delta T. So the key problem here is that when you land on the calcaneus, you don't really have much deformation of the calcaneus, because it's a really stiff material, you don't get the arch of the foot getting into the action. You don't have the Achilles tendon. You don't have the gastrocnemius muscles in the lower extremities. So what this means is that delta T, I'm going to have to move this because I got to do my color. Okay, sorry about that. There we go. There's delta T. So delta T is going to go down. Oh, I need another arrow, don't I? Let's get another arrow. Oh, I might as well make it a red arrow. Okay, that's working. I don't get paid by the hour, so it doesn't matter. Here we go. There's delta T. It's going down. So guess what's going to happen to the force? The force is with us. No, it's not. It's going way up. It's going to cause problems. So when the force goes up, that can potentially cause a lot of stress, potential damage to the foot, the ankle, etc. We don't have the arch of the foot protecting us. We don't have the Achilles tendon. We don't have the gastrocnemius or soleus or plantaris muscles. This is bad news. So we're much better off when we're running. When we walk, most people heel strike, not hopefully at this angle. That's kind of extreme. Hopefully something like this, where you land on the midfoot and the ankle should be underneath the knee so that the lower leg, the tibia, is fairly vertical. And what that's going to do is allow the arch of the foot virtually immediately to be able to deal with a lot of force. So when we looked at a force time graph, we could see a great reduction in that initial impact force. That's huge because, again, those muscles in the lower extremities, arch of the foot, especially with a heel strike position, they can't protect the body. They can't protect the foot, the ankle, the knee, the lower leg, etc. With a forefoot strike, now this is a little exaggerated. When you land on the forefoot, the shin, or I should say the lower leg and the tibia, is still going to be pretty vertical. So we've seen this in sprinters. But it does mean that when you're a midfoot or forefoot striker, your initial force is actually going to be just about straight down. Let's see if I can do that. There we go. Your initial force, and it's going to be over the arch of the foot. It might be slightly backwards, but it's not much with forefoot striking. If you look at sprinters who run on the balls of their feet, there's some argument that endurance runners should run like this as well. Not really on the ball of your foot, but landing on the midfoot and then immediately going into stretching the arch of the foot, which means the plantar fascia, the calcaneal and navicular ligaments. So it means that if we're looking at the reaction force, it's going to be pretty much straight up and down to begin with. And as they continue in the stance phase, what's eventually going to happen is that that impact force is going to be, sorry about that, is going to be, click on the right spot here. There we go. Is actually going to be downward, but it's also going to be a little backwards. And that means that the reaction force as during the stance phase, when you're running, you're starting to push off, and that means your body and lower leg are moving over the foot, which remains planted. So that means that the Earth's reaction force, we call it the ground reaction force, or GRF, Now that's going to be pointing forward, propelling you forward. In fact, that's ideally what we want to do, is load up the springs in the lower extremities, move over the ankle with a reverse pivot. Remember, we actually said that this is actually a special a special type of pendulum. We call it a reverse pendulum. So a regular pendulum, the axis of rotation's up high, and you kind of dangle back and forth like a grandfather or cuckoo clock. With a reverse pendulum, you actually land on your foot and then you pivot over the leg. This happens with walking and running. It's probably a little bit more important in walking than it is in running, but still it helps. It's another energy saving mechanism. So as we're pivoting over and doing, in a sense, a reverse pendulum, we have our action force that's down and backwards, and that means now the new reaction force is going to be up and forward. So there's the forward component. Your action force will kind of look in like that direction right there. Okay, so with midfoot striking, forefoot striking, those are huge advantages. With a midfoot striker, because the arch of the foot, particularly the plantar fascia, calcaneal and navicular ligaments, the arch of the Achilles tendon is also going to stretch, just like the arch of the foot. And that's partly because as soon as we land, our lower leg is starting to reverse pendulum or pivot over the foot. And that means that we're stretching the Achilles tendon immediately, the gastrocnemius immediately. So we've got a lot of advantages. We're now increasing delta T by deforming the arch of the foot, stretching the Achilles, stretching those muscles. So reducing that initial impact force, and measurements confirm that indeed this is not just a theory, and it actually happens. So physics is like that. Physics is really pretty good if your analysis and your math are good at predicting what's going to happen. As I said, particularly Newtonian physics, which is a little bit easier. Once we get into things like turbulence and subatomic particles and galactic related stuff, then things get weird. But in between, a lot of stuff is really, for the most part, predictable. This is actually really important when we're designing safety equipment, sports related equipment, prosthetic devices, artificial knees, etc. We have a lot of predictable forces that are going to be acting on the system. This is also important in analyzing the way tendons, ligaments, cartilage, muscles, bones, etc., how they respond to mechanical stressors. Okay, so pressure here would be the force exerted divided by that contact area. So if you're a midfoot striker, forefoot striker, you've reduced the force and you've increased the contact area. So if we reduce the force and increase the contact area, we see a double bonus, decreasing the amount of pressure. So that's what your feet like to see, because potentially those impact forces can be 2.5 to even 3 to even more times your body weight, especially if you're doing something that involves jumping, whether it is basketball or it could be volleyball or another sport. So you can see really super large forces. Okay, so let's do some calculations. David's standing, he's at Home Depot, so that each foot makes contact with the floor. Each foot has a contact area of 135 square centimeters when he's standing upright. If he has a mass of 60.55 kilograms, then what is the pressure exerted on the floor? That kind of looks more like 80. When the pressure is exerted on the floor. So remember, pressure is force divided by contact area. What we need to remember is that he is 2 feet, so we'll have to double this area, that contact area for each foot on the ground. We'll take the mass Remember, that's not a force. We'll have to convert it to a weight or force by multiplying that mass times the acceleration due to gravity. We've got 594 newtons. The contact area will be 2 times 135 square centimeters. And since there are 2 feet, the contact area is doubled. So that 270 square centimeters. We'll crunch those numbers and get 2.2 newtons per centimeter squared. And I wanted just to convert to standard units. So remember, we've got newtons per centimeter squared. There's 100 centimeters in a meter, but this is term is squared. So I've got to square that conversion factor. So I've got 100 squared centimeter squared in a meter squared. And that gives me 22,000 newtons per meter squared, or technically 22,000 pascals. Boom. Okay. Click up here. There we go. Let's do another problem. Let's say we have someone who's running, and this probably should be closer to 2.5 times her body weight, because I'm looking at her mechanics. It looks really good. Her foot's landing. You got that flex. We don't want to say bent. Remember, a bending force is something like that. You don't want that to happen to your knee, because you might be on YouTube the next day. And people go, "Oh, did you see that?" Oh, okay, so her running form looks pretty good. So this impact force may be closer to 2.5 times her body weight. I may change these problems a little bit. During initial impact, the contact area between the running shoe and the ground surface is 25 square centimeters. Find the pressure exerted on the running shoe's sole, and therefore her foot. A mass of 55 kilograms, an area of 25 square centimeters. Find the pressure for this runner. So multiply 3.5 times the body weight. Like I said, her form looks pretty good, so that may be a little excessive. It's probably closer to about 2.5 times. 3.5 times 539.55 newtons. That's her weight. Mass times acceleration due to gravity. And that gives me 1888.42 newtons. We'll divide by the contact area of 25 square centimeters. That gives us 75.54 newtons per centimeter squared. So I can convert here to standard units. Let's say that when she runs, she's got a new pair of shoes, and instead of having 25 square centimeters, maybe now she has 50 square centimeters. Well, that would reduce the pressure in half, because we have an inverse relationship between the area, contact area, and the pressure. Okay, the next application we're going to look at related to pressure is about pressure differences. And this was first quantified and theorized and measured by Bernoulli, who was a Swiss mathematician. I think he liked to gamble a lot, if I remember correctly. Some of the math that some of the mathematicians at the time were working on were actually to help them gamble better. That was part of what they were trying to do. So you can always apply math, and gaming is a good way to be able to do that. Allegedly in the 17th century when Bernoulli was around. Okay, so there's an inverse relationship between relative velocity and the relative pressure in a flowing fluid, and that could be air, that could be water. Regions of low velocity are associated with high pressure. Regions of high relative velocity are associated with relative low pressure. So not surprisingly, Bernoulli had an equation related to that we're going to look at now. As soon as this will cooperate with me. Let's try that. There we go. So you may have felt this if you open, a car door. You can feel that pressure difference. So what's happening is the air molecules are moving really fast, which is really fun for a dog when they stick their head out. They get to smell all kinds of things coming at them really fast, which is really cool. Plus, it feels nice and cool. It feels, they like it. They like checking out what's going on. My dog's the same way. There she is, Daisy. sneaking behind me. So the right side of this weird looking equation is a constant. That means it doesn't change. So what have we got on the left side? Well, if we break it down, it's actually not that bad. We got pressure. This is the density of the fluid. This is the elevation or altitude. This is the relative velocity. And then we'll divide by 2 times acceleration due to gravity. Okay, so in a given condition, so as this dog's going down the road, they've opened the window, we've got a pressure difference because the air is going past the window really fast. So it means there's low pressure and there's high pressure inside. So when you open the window, you actually get a burst of reduction of pressure because the outside's pressure is going to be lower. You're literally sucking air molecules out of the car. So if this dog is slobbering or eating something, it could go flying out. So if you're holding something in your hand, you open the window, it could get taken out pretty easily. So don't do that. Don't litter. Keep our highways safe and keep them clean. So what's really going on is when the air is moving quickly, there's less of a probability or chance that each air molecule will actually hit the car or hit the surface or hit the dog's head. The molecules on the inside, because of kinetic energy, they're moving around, but they're not flowing. So they have lots of opportunity to be able to hit the inside of the car window. So technically they'll have high pressure. So the Wright brothers originally started thinking about this late in the 19th century. And in 1903, they took their ideas and they knew they needed a lot of wind because the faster the air was moving, the greater the pressure difference was going to be. So as it developed a wing, looking at birds, they noticed, a bird's wing is able to stay in the air. So why can't a human be able to figure that out? Well, it had to do with when airflow is moving past this wing. We sometimes call it a foil design. It's round on top and it's flat on the bottom. That means those air molecules travel a greater distance on top versus on the bottom. What color can I make this? How about kind of a maroon there or dark red? Okay, distance divided by time. So we're moving a greater curvilinear distance. Doesn't matter whether it's rectilinear or not. Curvilinear distance on top. So that means that we have high velocity of the air molecules, and therefore the pressure of the air on top of the wing is going to be lower. So as this air is moving more rapidly, there's less of an opportunity for those air molecules to collide with the top of the wing. On the bottom of the wing, you're traveling a shorter distance for a given amount of time. Velocity is lower, and therefore the air molecules have a greater opportunity to be able to bounce against the bottom of the wing. The faster you're moving through the air, the faster the air is moving, the greater the pressure difference. So you have high pressure versus low pressure. If you think about weather systems where you have a high pressure and a low pressure or trough nearby, you get a big pressure gradient, and that creates a force, and that force blows the air and creates wind. And in one sense, you almost have the same thing here with a bird wing. You'll create a force that goes from high pressure to low pressure. Do it up there. There we go. I hate Times New Roman font. It looks good in an old book, but it doesn't really look good on a computer because the pixels on a computer are like X and Y. So all of the stuff that is supposed to help. Oh, by the way, the reason that Times font looks like this and print looks like this is there was, I would say from a scientific standpoint, we'll call it a rumor. There was a rumor in the 19th century and before that, that if you had something like a Times font, it made it easier in print to be able to read words. It turns out not to be the case, partly because the way our brain really perceives words is much different after we've done science and actually done the testing than people originally thought. Because when we read, especially after you're above second grade, you actually read through word recognition. So you read patterns. You probably have seen little experiments or little quizzes or puzzles where you're reading a sentence or a passage and they take out a lot of the letters. Most people can usually still read it because they recognize what the words are saying, they know about the context, and they can figure it out. So it turns out everything we thought we knew about reading and fonts was completely wrong. But here's the good thing. Steve Jobs took a calligraphy class way back in the day. So instead of the gnarly computer font, we only had like one or two fonts back in the 80s, or back in probably in the late 70s and at least early 80s. He developed lots of fonts. In fact, on my Mac, I have more fonts than I know what to do with. I've got about 40 fonts just for the letter A. It's ridiculous, isn't it? Well, I'm going to use Arial because I like that because it looks good on a computer. So there's my force. There we go. Bring it down there. So anytime you have a pressure gradient, you're going to create a force. The force will be with you. And in this case, the force is going to create lift because it's going from bottom to top. And that's what keeps the plane upright. Now, plane weighs a lot, and unless it's a Harrier jet, they can turn the engines 9 degrees. You're not going to get lift unless that vehicle is moving fast. So at ground level, you need about 120 to 140 miles an hour to be able to lift the jet. Once it's in the air, it usually reaches a cruising speed of 300-400 miles an hour, sometimes close to 500. You don't get to Mach 1, which is about 760 miles an hour, something like that. In the US, you're no longer allowed to break Mach 1 in a commercial jet. You used to be able to do that until sometime in the 1970s. Okay, so there's a different kind of bird. There is a jet. And the faster you move, the greater the pressure difference. So that's why it takes about 120 miles an hour to be able to take off. You create a nice big pressure difference. And that's based on Bernoulli's principle. So here's something cool. It's an upside down bird or airplane wing. And it is a spoiler. And the spoiler is really at the bottom. Or the spoiler is, again, an upside down bird wing. And you put it really over the back, usually near the near the back latch or near the trunk. And part of the reason it's in the back, so let me explain something. So a bird wing, hold on a second. Okay, a bird wing is round on the top, it's flat on the bottom. If we think about like a car or a truck, and let me see if I can grab one. I was going to try to get an entire car or truck in there. Let's see. Hold on a second. Okay, that one looks pretty cool. Let's just throw this up here. Oh, yeah. There we go. Come on. So what I'm getting to is that a car, especially a sports car, is flat on the bottom. It's round on top. This is a relatively aerodynamic design, so it reduces the coefficient of drag. The air exposed to the air molecules isn't that great in comparison with like a truck. But there's another thing that happens because the air is going over a round surface on top and underneath a flat surface, it creates some lift. And if there's too much lift, especially for a sports car. Now, a true sports car actually has rear wheel drive instead of front wheel drive. Rear wheel drive is harder to control. So that's why most cars and even many trucks today are front wheel drive or four wheel drive for some trucks. Rear wheel drive, there's a trade off in mechanics, and this is another one. So the trade off is you lose control, a lot of control. The chances of getting into an accident, especially on a slippery surface, are a lot higher. What you gain is a lot more torque. And so that's why drag cars, sports cars, real sports car. If you're driving a sports car and it's not rear wheel drive, it's not a real sports car. But again, you probably have to drive it a while to get used to it, and you're gonna have to be careful because it can fishtail like crazy. Okay, so you actually potentially have lift. So if there's too much lift, especially with rear wheel drive, it gets slick, it gets slippery, and you lose control of the vehicle. So some of the sports cars can be pretty expensive. So that doesn't really sound like a good idea. Plus, you have other people on the road, so we want to be as careful as possible. Okay, so that's why a lot of sports cars or fake sports cars, this looks like a fake one to me. I don't know. This could be real. Is this a Porsche? I'm trying to look. If it's a Porsche, it's a real one. So the reason they have spoilers is to actually, with an upside down wing, is to create a force going from top to bottom. We basically flip the wing upside down. So we've got this pressure difference created by Bernoulli's principle. And there's also a trick related to turbulence. So in a bird wing or an airplane wing, there's a little bit of turbulence on the bottom, right on the back end, right here. We grab a T, and of course it's in times font. I keep trying to change the default, and it doesn't work. Okay, so there's an area of turbulence right under here that actually helps with the lift, because the turbulence slows the air molecules down even farther, and so they collide more with the bottom of the wing near the tip. For a bird, it's got this as well. So the tip of their wing becomes really important, and birds can basically guide that to be able to speed them up, to be able to slow them down, and they can really finally control their airspeed. So it's not like you're flying in an airplane where you're going at a constant rate, then you can kind of slow down a little. Birds can move really quickly and dart to the left, right, up, down. They have a lot of control literally at their wingtips. And their wingtips also have these grooves that we talked about before a little bit when we were talking about cycling helmets that provide laminar flow on top, and then you get turbulence on the bottom. So it's something that's really in addition to a pure Bernoulli effect, but it also feeds into the Bernoulli effect because it slows the air molecules down, giving us low velocity on the bottom, high pressure, and then low pressure and high velocity on the top. Okay, but as I was saying, with a spoiler, so that's why we have a spoiler alert here. Spoiler is an upside down wing. So the turbulence is a little bit on the top. The airflow is going to be slower on top than on the bottom. So that means that there's a force being generated down the pressure gradient from high to low. So instead of a bird wing where the pressure gradient is low on the bottom, high on top, what did I say? The pressure gradient is, I'm sorry, high on the bottom and low on top. I was thinking about the velocity, sorry. You're going from high pressure to low pressure, which means upward. But with a spoiler, which is an upside down bird wing, you got force being created from the high pressure on top versus the low pressure. Okay, so why do they do that? Because that low pressure pushes down on the tires and creates more traction between the tires and the ground. So that's why they have a spoiler. Even let me find a drag car picture. Yeah, check out this one. This one's kind of exaggerated, so let's see what we've got here. I'm going to. Oh, I forgot where I am. This, how do I? Oh, it's because I'm on Chrome. Okay, duh. There we go. I'm going to just duplicate a page and just do that for a second. Okay, here we got a drag car, and it's got this huge spoiler on top. You may have wondered, what the heck is that thing doing on top? So the purpose here is this thing is going really fast and it's rounder on top than the bottom. So the faster you're going, the more lift it's going to create. So you're trying to keep this thing on the ground. You probably noticed with sports car, race cars, NASCAR, etc., that these cars become really unstable. They get bumped just a little bit, they just start flying up. And you would think, well, things moving really fast, the inertia should keep it, right there on the ground. But if you create a little bit of space and you get that little bit of gap underneath, and your spoiler's not working quite right, you get unstable, that lift is going to take over and it flips the car and you get, horrendous accidents. So what this is doing is this is allowing, you probably notice when this thing starts up, it's going to do a wheelie on the back wheels. That's where the drive is. These front wheels might even go up in the air, but this downward force is going to maximize, especially as this thing is moving, maximize the amount of, we're going to call it Bernoulli's related force, Bernoulli force, pushing down. Can't really call it lift because it's not lifting it up. It's reverse lift, if you will, but it's pushing down on this drag car, and it's going to keep those rear wheels, which are the drive wheels, on the ground. So this thing can go really super fast. Okay. Oh, that was fun. That actually fills in our gap, believe it or not. So we can take it home, man. And we put, I'll move the screen. There we go. Because I can. I'm doing this because I can. Well, that kind of works. All right. Okay. That's it. That's all the lectures. I think the rest of them are filled in over the past year. It's been an amazing year, literally, in so many ways. So we'll keep these for posterity and use them wherever we can. You guys have a great one. We'll see you again soon.